Hey, just carrying on with our videos for functions of multiple variables. This video we're going to be looking at stationary points of a function of two variables. Just to remind you, last time we went through different functions expressed in different ways of multiple variables. We went through solving them, and for this video it's just going to be of two variables. So we have a problem here, a function of x and y which is equal to x cubed plus xy plus y squared. And we're going to try and find all of the stationary points. Now I've drawn a admittedly bad drawing of what a stationary point might be. So if we have like a plane here, and a stationary point here would be a local minima dipping down in the plane, and just you could have like local minimas and local maximas. And there's also a point called a saddle. The best thing really to do is have a look on Google and have a look what a saddle, local minima and local maxima look like for a function of two variables, and you'll get a good idea there. So we have a step-by-step procedure for finding stationary points, and also what I'd always recommend to do is take a page and you make certain notes which you'll be constantly referring back to, and you don't want these mixed up in all your workings. So I always like to take a page out and put it to the side. So the first thing we have to do is find the derivatives with respect to x and y twice, and then the mixed. So with respect to x, respect to y, x twice, y twice, and then the mixed, where remember, either way is going to give you the same answer. So first with respect to x, so we get 3x squared. Remember our y is constant, so just plus y, and that vanishes. Now with respect to y, that vanishes, and we're left with x plus 2y. X twice is going to give us 6x, and y twice is just going to give us 2. And then on mixed, we have a look at our x or our y and differentiate with respect to the other one. And I'm going to take the y and go with x, and this just gives us 1. Okay, so that's nice and easy. And then what we need to do is move this to the side, and next we're going to look and we're going to find that our, with respect to x once and y once, are both equal to 0. So if we do this, we say that 0 is equal to 3x squared plus y, and 0 is also equal to x plus 2y. If you're in an exam, make sure you write that down, don't just skip that, because you often get marks for things like that. And now also you want to solve this in terms of, well, I'm going to solve it in terms of y, so y is equal to minus 1/2 x, just there. I'm going to substitute this value in here for y, so 0 is equal to 3x squared minus half x. I'm going to make life a bit easy by multiplying everything by 2. So 0 equals 6x squared minus x, and then just take x outside. Really, I don't need to go through step by step for this. Hopefully you've done this kind of thing before. And then we can see that this is only true if x equals 0, or if x is equal to 1/6. There. Now we do is just punch in our values of x into this equation here, because this is a nice one. So 0 is equal to 0 plus 2y, therefore when x equals 0, y is equal to 0, and 0 is equal to 1/6 plus 2y, then when x equals 1/6, y must be, or minus 1/12. So now we've found those, we can write that down, and we can say that we have 2 points, point 1 and point 2, and point 1 is 0, 0, and point 2 is 1/6 minus a 12th. So what I'm saying about keeping a sheet, because you will be referring back to it a lot. The next thing then is to find an equation for d. So d here is equal to f of xx by f of yy minus f of xy all squared. Okay. So what we're going to do now is we're going to look at our second derivative of x here, which is 6x. Multiply that by our second of y, which is 2. and then take away our mixed squared, which is just 1, and then we can rearrange this to be 12x minus 1. So this is D. So our equation for D is equal to 12x minus 1. Next thing we need to do is find D1 and D2. So D1, so punch in both of our values. So we have, well, 12 by 0 is 0, and then minus 1, so this is minus 1 here for D1. So D1 is equal to minus 1. And for D2, we put in the value. Now it only has an x there, not a y, so we can put in our value here. So we have 12 over 6, looking at that one up there. 12 over 6 minus 1, which is equal to 2 minus 1, which is equal to 1. So our D2 is equal to 1. Now we have to analyse our points. So this is where the second part comes in. So if D is less than 0, it's a saddle, and if D is more than 0, it's a min or max. So first we'll have a look at these, and we can see that D1 is less than 0, so that's automatically a saddle. And D2 though, that's more than 0 because it's 1. So 1 is more than 0. So then we need to look at the second derivatives with respect to y. It doesn't matter, and I'll show you that now. So what we do is we take f of xx or f of yy, and for each of these we punch into whatever the values for the point we can. So f of xx is 6x, where x is equal to 1/6. So this is just equal to 1, and this is more than 0. And the second for y is just 2. There's no variable there. So then this is also more than 0. This is always true. They're not going to be equal, but they're always going to be either both more than 0 or both less than 0. And since these are both more than 0, then this is a minima, similar to when you're finding stationary points of one variable. So this is a min. So what we can then say, we can deduce from this that point 1 is a saddle, and point 2 is a local minimum. And that is how we find stationary points of a function of two variables using a two-part method. Just here. Anyway, if you want to see the last video in the series or the next video in the series, just go ahead and click there. And if you want to see more from my channel, just click down the bottom.